In our last episode, we successfully converted Sabrina's lyrics into numbers. We took raw words, split them into subword tokens, and mapped them onto a multidimensional spatial map called an embedding matrix. But now we have a major problem. An embedding layer looks at tokens entirely in isolation. It treats sentences like a random bag of words, completely blind to their order. For example, if Sabrina sings, "Now he's thinking about me," that means one thing. But if we flip the exact same tokens around to say "me, now he's thinking about," the grammatical flow is ruined. Or worse, if we take the phrase like "not bad, actually good" versus "good, actually not bad," they mean completely opposite things. Yet, to our static embedding matrix, both sentences look identical. Because the model doesn't know which token came first, it's virtually deaf to the syntax of the lyrics. If we want our LLM to understand context, we need to do two things today. Give our tokens a sense of time and build the actual engine that lets them talk to each other. So how do we give our model a sense of order? We need positional encodings, the next step in our GPT architecture. If we have the sentence "not bad, actually good," we want the model to know that "not" is at position 0, "bad" is at position 1, and so on. Our first instinct might be to just add the index number 0, 1, 2, and 3 directly to our embedding vectors. But think about what happens as sentences get longer. If a sentence has 1,000 tokens, the values at the end of the sequence will be massive compared to the beginning. This completely breaks the stability of our neural network's weights. To solve this, we need a more clever way to encode positional information. To this day, there are three main ways of doing this. The first one is to use absolute positional encodings. We assign a unique fixed signature vector to every specific index in a sentence, which is what we are about to do today. Early pioneers like BERT and GPT-2 relied entirely on absolute positions. The second one is to use relative positional encodings. Instead of marking fixed spots, we explicitly measure how many steps away tokens are from one another. And lastly, we can also use rotary positional encodings, the modern standard used by models like Llama, where we literally rotate the token vectors in space by a specific angle based on their location. To keep our architecture clean and elegant today, we're going to implement absolute positional encodings. While rotary positional encodings is the golden standard for modern LLMs like Llama, learned absolute positional encoding is the simplest and most intuitive way to build a model like GPT-2 from scratch. So the idea is that we need to generate a unique positional vector for every single index in our sequence, and we add it directly on top of our token embedding vectors, element by element. Models like GPT-2 initialize positional vectors with random values and let the model learn the best position embeddings directly during training. Instead of manually engineering clever math formulas, we literally instantiate a second lookup table just like our word embedding layer. One table maps token IDs to vectors, and the second table maps position indices to vectors. Then, we look up where each token sits in the sequence, put its corresponding positional vector, and add it directly to its word embedding vector, element by element. Now you might ask, doesn't adding numbers directly on top of our word embeddings corrupt the original meaning of the word? The magic happens in high-dimensional space. Because vectors in high-dimensional spaces have immense capacity, the model learns during training to reserve certain subdimensions for what the word is and others for where the word is. They coexist cleanly without wiping each other out. Let's put this in LLM model positional PY. We'll build a module that, given a D submodel and a maximum length, builds a positional matrix we can add to our token embeddings. We will first import Torch and the neural network submodule, torch.nn. Now let's implement the class that will add a positional encoding to our input embedding vector x. In the constructor method, we create the positional embedding vector and save it in the attribute PE. Now, every time we use the forward function from the class and input an embedding vector, it'll add the positional encoding. Now let's code the demo so you can try that at home. It'll be saved in script as demo_positional.py. If embeddings give us the meaning of a word and positional encodings give us its location, self-attention gives us its context. Imagine the sentence, "The river bank flooded." How does a model actually know the difference between a bank as a river edge versus bank as a financial business? The idea is that it projects our token embeddings through 3 separate linear layers to create 3 distinct vectors for every single token: a query, a key, and a value. Think of every token as a vector pointing in a specific direction in a high-dimensional space. To create a query vector, we multiply our token vector by a learned weight matrix W sub q. The query represents what specific information a token is looking for, while the key represents what attributes or context a token offers to others. In plain terms, the query represents what attributes or information the token is looking for. To create the key vector, we multiply the token by a separate matrix W sub k, which maps it into the region of space describing what the token actually is. When we calculate Q times K transpose, we're taking the dot product between the query of word A and the key of word B. If the query arrow and the key arrow point in the almost same direction, they mathematically align, producing a massive positive score. If they are perpendicular or point away from each other, their score drops towards 0. To keep these dot products from getting too large and stall learning with near zero gradients, which would cause the softmax function to saturate and stall learning with near zero gradients, we scale the scores by dividing by the square root of d sub k. After applying softmax to our scaled scores, we get an n times n probability matrix, which is our attention map, where every row sums to 1. While Q and K are strictly used to calculate the routing weights, V holds the actual content payload. We need to multiply the attention map by V to extract and blend those contextual features. For any given token, this matrix multiplication computes a weighted sum across all value vectors in the sequence. The result is a context vector, an updated representation that bends the static meaning of a word with the exact information it needs from its surrounding tokens. Mathematically, this entire operation compresses into the classic scale dot product attention equation from the 2017 paper, "Attention is all you need." To see this in action, let's walk through the previous 4-token sentence. The river bank flooded. Here, the word bank changes its meaning entirely based on its context. Each word starts as a simple 2D vector, that is, d submodel equals 2. After projecting our embeddings, we get our 3 matrices. Remember, query is for what we're looking for, key is what we advertise, and value is the content. We compute the dot product between the query of bank and all keys, and notice that bank aligns strongly with flooded and river. After dividing by square root of d sub k and applying softmax, we get our attention weights for bank. Finally, we calculate the weighted sum of values. Great, let's put this math into code. I'll put the code in LLM/model/attention.py. Now let's implement the class. In the constructor, I'll create 3 linear layers, W sub q, W sub k, and W sub v. Each maps d submodel to d submodel and learns how to build queries, keys, and values. In forward, we project X, compute scaled scores, softmax to get attention weights, and then mix the values. If we just let the attention mechanism look at the entire sentence at once during training, the token at position 2 could easily look ahead to the key at position 3. The model would literally cheat. It would just copy the next token instead of learning how to predict it. To stop that, we need to apply a causal mask. If we take our attention score matrix and block out the upper right triangle by filling it with negative infinity, when we apply the softmax function, those negative infinities turn exactly into 0% attention. That's how the model is now physically blinded to the future. It can only look at the tokens that came before it. Let's update our attention module so it can't look ahead. After we compute the score matrix, we built a Boolean mask with torch.tryU. Everything strictly above the diagonal is the future. So we fill those scores with negative infinity. Softmax then turns those into zeros, so token I can only attend to tokens from 0 to I. That's causal self-attention, the same constraint GPT uses when predicting the next token. We have officially coded positional encodings and implemented a fully functional causal self-attention layer from scratch using raw PyTorch. All the code that we did today is pushed to the GitHub repo linked in the description below. And as always, if you have any questions, drop a comment in the comment section below. I'll see you in the next one. Bye bye.